Hello there, this is Dr. Dell, and this is going to be the introduction to geometry. Now, we briefly looked at what we're going to cover in geometry in the overview of Tier 4, but now I'm going to talk to you about geometry in quite a bit more depth to get you set up for this presentation that you're going to get in geometry in Tier 4. Well, as you know, we covered quite a bit of geometry in Tier 2 in the Practical Math Foundation, which you've already had. And geometry is the study of triangles and circles and cones and spheres and parallel lines and things like that. But now we're going to study it in more depth out of Dr. Simmons' book, Pre-Calculus Mathematics in a Nutshell, which really starts right off with geometry. Okay, the first thing that I would like for you to do, if you haven't done so, is open up Dr. Simmons' book and read the preface, which is really a preface to the entire book. And then I want you to go over to page 2 and read his introduction to geometry. I'm not going to read it for you, so I want you to pause the video if you haven't done so and read this in depth, and then I'm going to discuss some of the features of it with you. Okay, Dr. Simmons says that geometry is a very beautiful subject whose qualities of elegance and order and certainty have exerted a powerful attraction on the human mind for many centuries. And I agree with that 100%. It's a fact, it's true. And in fact, he goes ahead and begins to talk about classical civilization. He's really talking about the Greek civilization. And I will tell you now that the very first treatment of geometry that we have, that a lot of our modern books are based on, was called Euclid's Elements. Now, Euclid's Elements, I got this off of Wikipedia, so you can go and look this up, and this is just the first page. Euclid's Elements consisted of 13 books that divided geometry into a whole bunch of different categories. And what he starts off with are assumptions, which are called postulates and axioms, and then using logic, Aristotelian logic we call it, Aristotle's logic, he began to prove theorems. And that's what these books consist of. And as a matter of fact, they influenced human beings and mathematicians for many, many centuries, really well over 1,000 years, and well up into modern times. And even today's geometry books have their roots and a lot of similarity with Euclid's Elements. You could go to the library and probably get a copy of this and look it over, and you would find it to be, I think, very interesting. Now, in his introduction, if you go back and reread it, one of the Greeks that Dr. Simmons refers to is Archimedes, who actually made some of the most profound discoveries in geometry. He came a little bit after Euclid, of all of the Greeks, and in fact is considered one of the 3 greatest mathematicians of all time by modern mathematicians and historians. And once again, you could learn all about, or a lot about, Archimedes at Wikipedia, which I find to be an excellent resource. And indeed, Archimedes made discoveries that I even talked about back in Tier 2 with Archimedes' tombstone that you might have found interesting. And indeed, in Dr. Simmons' book, we're going to look at proofs of a couple of those things that are usually not uncovered in geometry and that I think that you'll find very interesting too. Now, you may have noticed that these Greeks did a lot of this mathematics in 300 BC and thereabouts, and so that was about, as you can tell, over 2,000 years ago, BC meaning before Christ. And then Greek geometry and mathematics really dominated mathematics and science for about 2,000 years, up until the 1600s, the 17th century, and mathematicians and scientists began to discover additional things. Algebra was introduced from the East, as were our modern number systems, the decimal number system, for example. And then Isaac Newton discovered something called the calculus. He was from England, and in the continent over in Germany, a guy by the name of Leibniz also discovered similar things, the calculus, which we'll be learning all about in Tier 5. And in fact, Newton and Leibniz turned out to be rivals. There was a lot of competition back in those days. And so both of these gentlemen are given credit for the invention of calculus. And indeed, Leibniz's view of calculus and even his notation carried through to modern times more than Newton's did. And indeed, Leibniz even made some discoveries that didn't get fully understood and implemented until really about 50 years ago in the 1960s. Now, Newton is the much more famous scientist than anyone else of his era. In fact, Newton is considered to be really the father of modern science. He really launched what we would call the modern scientific revolution. There were other people like Galileo that preceded Newton that certainly contributed, but Newton published a fantastic book, became the most important book in the history of science, called Principia Mathematica, Mathematical Principles of Natural Philosophy, in 1687. And this laid the foundation for classical mechanics, and you can read about that on Wikipedia. And he used calculus to do it. In fact, he made his discoveries with calculus, but he didn't use them in the presentation of that. As a matter of fact, if you would go get a copy of Newton's Principia, which I did many, many years ago, I thought, well, I want to learn physics. Maybe I should learn it from the master. And I went and got a copy of Principia and started studying it, and I was absolutely amazed even to find that it was just full of geometry. As a matter of fact, there was no mention of calculus in this book whatsoever. It was strictly complex geometric constructions, just amazing, and they were not easy to understand, I might add. I'm pretty good at geometry. I liked Euclidean geometry when I was a student because I had a very good teacher, Madonna O'Hare, and so I really enjoyed proving theorems. Many people don't enjoy that so much, as Simmons points out, and it discourages them, and for good reason. If it's not taught really, really well, it can be horrible, and it usually isn't taught very well. But in Newton's book, what you see in Principia is just nothing but a bunch of Euclidean geometry type constructions. And some of them are really, really quite complicated. Pretty amazing, actually, if you read it here. Look at this one. Now just imagine that this is a geometric figure, and notice all these letters. So they're denoting different line segments and angles and all of this, and these are circles. And Newton is giving you an argument about physics. This is all about physics and astronomy, and Newton is the one that discovered that Kepler's laws of motion for the movement of planets were accurate, and he proved it based on the principle of gravity and Newton's, what are called Newton's laws of motion. So it is really a remarkable book, but by modern standards it's extremely difficult and obtuse. This is not, in fact, how I learned physics at all. I found this book to be basically useless for me because it was just too archaic. But that shows you how important and powerful the Greek influence was, because even when Newton decided to write up his wonderful discoveries he had made with calculus, he actually proved everything using geometry. Well, while we're looking at the history of things, let me point out that one of the really great mathematicians of all time also was a man by the name of Euler, and he came in the 1700s. He came after Leibniz and Newton, and he was also on the continent in Europe, and he was in fact probably the most productive mathematician of all time. He has written more original mathematics than any other mathematician in history by far. Just truly, truly amazing. And in fact, he is the man that then took Leibniz's work, turned it into what is modern calculus and differential equations and a whole lot of other things. And in fact, he used techniques in the 1700s that mathematicians, for various technical reasons, abandoned in the 1800s, and they weren't reintroduced until the 1960s, right when I was in graduate school. It's just absolutely amazing what Euler did. And as far as mathematics goes, he is probably kind of the father of modern math, as we're going to be learning it in tiers 5 and 6, as well as parts of tier 4. Well, now you might very well ask, how should one learn modern physics using modern calculus and mathematics? And my answer would be look up Richard Feynman, F-E-Y-N-M-A-N, on Wikipedia. Richard Feynman was one of the very great physicists who lived in the middle part of the 20th century. And in the 40s and 50s, he discovered a fantastic way of treating what is called quantum theory, or quantum electrodynamics, QED for short. And he won a Nobel Prize for that. And then as a professor of physics at Caltech, he actually gave a series of lectures in the early 60s that are now called the Feynman Lectures on Physics. And there are 3 volumes. This is volume 1. And they're not easy to learn, I will tell you, but after you've had mathematics up through tier 5 and 6 in my class, you will be able to probably follow these. And if you would get them and look at them, you'll see while there is some geometry in them still, there's also a lot of calculus now, the way it is now taught in the modern world. And so you will be able to learn physics this way. In fact, there will be easier physics books to learn physics from. This is an extremely in-depth treatment of physics, and even though it's 50 years old now, for basic physics, it's still extremely valuable and modern. And I don't know a lot of physics today, but what I have learned, mostly I've learned out of Feynman's wonderful book. And so I think that you would enjoy that very much if you wanted to learn physics. Now, before I depart the discussion of Richard Feynman, we'll point out there were 3 volumes in this series. It took him 2 years to deliver these lectures, and then he had a lot of assistants helping him write them up. But if you want to learn a lot about modern physics and how mathematics applies, you might get the popular book called Surely You're Joking, Mr. Feynman by Richard Feynman. And it's really written for the lay public, and it's a lot of fun to read. And Richard Feynman will tell you all kinds of interesting stories. In particular, he worked on the Manhattan Project when the atomic bomb was being developed, and he can tell you a lot of stories about that. And then if you're interested in modern physics, and in particular if you want to know about quantum theory, which, by the way, quantum electrodynamics is the subject that really explains, that underlies all of modern chemistry and lasers and modern technology. And Richard Feynman gives a discussion of that you can understand. It's in 3 lectures. It's called QED, and it's a short, thin book that I'd highly recommend to you. And in fact, once you study complex numbers in our tier 4, you'll see how they apply to QED. He doesn't talk about them specifically in here, but he uses an analogy that you'll recognize, and so I'd highly recommend that to you. Mathematics opens up so many, many subjects to you, and physics is just one of many, many subjects that mathematics opens up. Okay, now you've got the contents of what we're going to cover in geometry out of Dr. Simmons' book, with a few lectures that'll have notes from me, but the bulk of this will come from Dr. Simmons' book. And it's, as he points out in his introduction, if you go back and read it to geometry, he covers all of this in, let's see, how many pages? This is page 33. So he covers all of this, including exercises and appendices and everything he does, in just like 20 pages or so. It's just absolutely amazing. And this, frankly, is all of the regular Euclidean type geometry you'll need to know. Some of this you've learned already in the Practical Math Foundation course, but a lot of it you haven't. And in fact, there are some remarkable proofs in Dr. Simmons' book that I've never seen covered in any high school geometry book, and I'm going to cover them with you, for you, thanks to Dr. Simmons. In fact, you know, I have a PhD in mathematics, and when I read this book for the first time, I was amazed at some of the proofs he gave, things I had never seen in any high school book, for how to derive the area and the volume of cones and spheres. It's just truly amazing. This is a wonderful, wonderful treatment. We will be proving theorems, but not in a formal, pedantic way, but in the way a mathematician proves theorems, with logical reasoning, precise reasoning, complete reasoning, and yet it's not difficult really to understand. So this is going to be a lot of fun. You're going to learn a lot in these upcoming lessons. Okay, now as you see here, there are going to be 20 lessons altogether, including this introduction. And go back and watch the video where I taught you how you should study. It's very important you do this right. It'll be, I won't say easy, but it'll be very doable for you if you do it in the right manner. So watch the video where I discussed how you have to learn math and study math, how we all do. And then I'm sure you'll be very successful. And this will lay a great foundation then for the rest of the math you're going to be learning.